Okay, people always wonder how to determine a hypothesis test just from reading a statement. Now, key things to remember about a hypothesis test is that if you have a hypothesis test, then you're actually testing for a parameter, and the parameter is claimed to be a certain value. In other words, if the parameter is mu, which is the population mean, I can make a claim about the mean. And if the parameter is p, which is population proportion, then I can make a claim about the population proportion. But what sort of claim could we make? Both mu as well as p are numbers. So when it comes to numbers, there are only a few possibilities of claims that we can make. So let's just take mu for instance. Since mu is a number, I can claim that the population mean is equal to another number. Let's say mu naught. Let's say mu naught is another number. The only difference is that mu is not known because it is the population parameter. It's not known, so I can just write it as a notation. But mu naught, on the other hand, it is a claimed value. It is known. So, if I start with this claim, mu is equal to mu naught, the counter argument to that is mu not equal to mu naught. Likewise, if I stated that mu is less than or equal to mu naught, which means at most mu naught, the alternative is mu greater than mu naught, which would be another statement. In a similar manner, if mu is greater than or equal to mu naught, which is at least mu naught, when I say at most mu naught, meaning to say mu is at most mu naught and mu is at least mu naught, and I could come up with another counter argument that mu is less than mu naught. So in total, if you counted, you'd see that there are 6 logical statements: mu equal to mu naught, mu not equal to mu naught, mu less than or equal to mu naught, mu greater than mu naught, mu greater than or equal to mu naught, and mu less than mu naught. Now, having said that, we don't want to test for all 6 statements. Now, all 6 statements can be narrowed down to 3 logical statements. For instance, if I started by saying mu is equal to mu naught, if I set that as the first statement, the counter argument is mu not equal to mu naught. So out of the 6 logical statements, I've taken care of 2 of them. Now, if you see that I'm using a very standard approach here, H naught is nothing but the null hypothesis, and H1, sometimes called as HA, is called as the alternative hypothesis. So if someone claims that mu is equal to 5, suppose, for example, if mu is claimed to be 5, then the hypothesis is mu equal to 5 versus the alternative mu not equal to 5. So the claim would be in the null. In other words, the claim is represented by the null hypothesis. You can perform a hypothesis test, and a sample might either agree with the null or it would agree with the alternative. If it agrees with the null, then the claim is true. Your sample supports the claim. If it agrees with the alternative, then there is not evidence toward the null, rather the evidence is toward the alternative. In a similar manner, we can construct and obtain the other statements as hypotheses. So, for example, if the claim is mu less than or equal to 0. So if you started with less than or equal to 0, the null is less than or equal to 0, the alternative is mu greater than 0. Just by having this one hypothesis, I can verify two statements. For example, if someone presented a claim, if mu is claimed to be at most 0, in this problem the claim is represented by the null. So you collect a sample, you perform a test, the test would either agree with the null or it will agree with the alternative. If the test offers evidence toward the null, then the null is accepted. You don't reject the null. If you don't reject the null, you conclude that the claim is true. But if the sample supports the alternative, then you can say that mu is greater than 0 and the claim is no longer true. So if sample supports HO via a hypothesis test, then claim is true. But if it supports H1, then the claim is not true, because in the problem we have claimed that the null is what is considered, and the null is supposed to be true because that is the claim. Now, we can extend the idea into one more case where we can say, suppose that the claim is the population mean, mu, is greater than or equal to 9. So mu naught is 9, which is the claim's value, and that is the population parameter, which is the population mean. So if I want to test a statement, all I have to do is perform a test with this hypothesis. Mu is greater than or equal to 9 versus the alternative, that is H1, mu less than 9. The claim is represented by the null, and if the sample supports the alternative via a hypothesis test, if you perform a hypothesis test and the test supports H1, then we reject null, and if we reject null, we actually end up rejecting the claim. So we did not find evidence toward the claim. So in summary, we have a parameter and we'd like to verify the claim made about the parameter using a sample via a hypothesis test. In doing so, we have come up with three scenarios. One is mu equals to mu naught versus the alternative mu not equal to mu naught. The other is mu less than or equal to mu naught versus the alternative mu greater than mu naught. Mu greater than or equal to mu naught versus the alternative mu less than mu naught. These three statements, these three hypotheses would help us in testing all 6 logical statements that I first started with. Each of these hypothesis tests have a name. The first one is called a two-tailed test. The second is called a right-tailed test. And the last one is called a left-tail test. In most cases, I just observe the arrow in the alternative, or not to say the arrow is actually the symbol in the alternative, and if the mathematical symbol, which is a greater than here, if it's pointing to the right, then it's a right-tail test. I look at the alternative, and if the symbol is actually pointing to left in this particular scenario, so I conclude it's a left-tail test. That is actually an easy way of remembering what test you're performing. And a key observation is that if you observe that the equal sign appears in the no, a common misconception is that the equal sign could fall anywhere, the no or the alternative, but that is incorrect. The equal sign must always appear in the no, because from a mathematical standpoint, it is what we call the reference distribution. So the equal sign should always appear in the no. You can test other parameters such as population proportion. So if you want to write hypothesis definitions like I did here for 3 cases, but if you want to do it for population proportion, all you have to do is change the mu's by p's, and then you have a definition for a population proportion. Now, this is a very general introduction to hypothesis tests, but of course there is a lot of mathematical theory that is involved in hypothesis testing, but this particular video would only give information about how to identify the right definition for a given particular problem, and how to write the definition and proceed with the correct test so that you have a proper conclusion for the problem at hand.